Hi guys, welcome you back to my another video. In this video I'm going to talk about the synchronous reset and asynchronous reset. So first let's talk about this. So synchronous reset are those signals that the reset will only affect or reset the state of the flip-flop on the active edge of the clock. So it can be at the positive edge of the clock or it can be at the negative edge of the clock. Whereas for asynchronous reset, it is a reset that the flip-flop does not wait for the clock and set the output right at the edge of the reset. So it means your circuit should reset whenever reset signal is active, irrespective of the clock. So for asynchronous reset, it doesn't depend upon the clock, but for synchronous reset, it depends upon the clock. So let me show you one image for this example. Now this is a clock and this is a reset. So we consider that this is a active high reset. Now once the reset is deasserted, this is the input data and this is the output data. So the moment the reset has been deasserted, we can see here the data, input data is randomized. Okay, in the code I will show you this. It is randomized and then this data will be assigned to the output data. So this is the output data. So in order to get in the output data, this output data need to wait for the next clock cycle, next positive edge of the clock cycle. Okay, so here in the first clock cycle, the data has been randomized, but in the output we are not getting because the reset is still high. Now once the reset has been deasserted, then in the next clock positive edge cycle, we are getting the output data. This is the synchronized. Okay, the synchronized will depend upon the clock. First of all, I'm going to use the flip-flop as an example for this one. So let's start with module and then write down the name of the module as the flip-flop. In the port list, we'll declare the signal clock reset. So in data and out data. Okay, so these are the signals we require and module, and we have to declare it as input or output. So input clock as this clock and reset are 1 bit, and let's give as in data as 4 bit. Okay, I'm going to use 4 bit, so 3 down to 0 and then in data. Okay, and for this out data, this is the output signal, so I'm mentioning output, and make sure that output signal need to hold the value, so we have to give it as register reg. Okay, and that is all. So 3 down to 0, that is 4 bit for out data. As I'm going to use the procedural statement, so always at the rate of post edge clock. First I'm going to do this for the synchronous. Okay, synchronous reset. So at the positive edge of the clock, begin and we have to give the statement if reset is active high. Okay, let's begin and we'll make this one as, so we are giving this out data is assigned with 0. Okay, fine. If the reset is high, we are setting the out data as 0. Now else begin and we are going to set out data with the input data, that is in data. Okay, so this is the RTL design for the flip-flop, which we are going to verify it for synchronized reset. Now we'll go to the test bench and start writing for the test bench code. Module test bench top and module. So here we have to declare the signals which are being used here in the RTL. You can use any name, but I want to use the same name for the design as well as for the test bench. Now For input, we have to mention it as reg clock reset. Okay, and then we have to give for the in data also, in data. For output, we have to mention it as a wire. Out data. Okay, now once we have declared the signal, we have to instantiate this design into the test bench. So the name of the design is DFF, right? So DFF, and instance name we have to give instance. I can use this inst, and then I'm going to instantiate by using the position. Okay, like clock is the first one, second is reset, like the same in the same position. I'm going to use it out here. Clock reset in data and out data. If I have replaced, if I have not given a proper position, like this example, if I take this out data in the third position, then there will be an error. So if you try this by your end, okay, and check it out once. We have instantiated design, so we have called the design in the test bench module. Now we are going to generate a clock. So initial, begin, and then the clock initially we are assigning with 0 value, and later on forever hash 5 nanosecond. Okay, that is delay, clock, and negation of clock. So this will generate the clock signal. Now we are going to give for reset, we are going to apply for reset as well. Initial, begin, and reset equal to 1, as we are dealing with active high reset. So reset is 1, it is active high. Okay, remember this. So initially I'm starting with the 1 value, and then delay of 5 nanosecond, and then after 5 nanosecond I'm resetting the signal to active low. Okay, so this is the portion for the reset signal, and let's just give some delay. After 3 nanosecond I'll just stop this reset. Now I need to apply the inputs, right? Apply the inputs for the D-in to randomize, to give a random value for this D-in, so that whatever generated by the D-in value will be given to the out data. So here let's repeat for, let's say 4 times. We want to repeat for 4 times, and then let's say here, let's give it at pause edge. Okay, pause edge of clock, begin, and then we will give in data with random values, $random. Okay, so by this it will give a random values 4 times. It will generate a random values 4 times. Now after this, what we want to see, we want to check the waveform, right? So we have to use this to check the waveform, $down file, and then let's just give name one as test. Down variables. Okay. Now after this, we have to select the EP waveform, and then we have to select the tool as well. So this is the tool we want to select as mentor requester, and then EP waveform after that. Okay, so this will be the, okay, this will show us the waveform. Now let me compile this, and then let me run this also. There is no error, 0. So Actually, there is no waveform because I missed out one important thing. See, this is the clock, right? So it is in forever loop. So we have to stop this, okay, by using one operation called as $finish. So here, let's write one more initial begin block. Initial begin end. So this is very important that I missed out. So here we have hash 100 nanosecond. Let's make it after 200 nanosecond. You want to finish the clock. So let's save and let's run it. Okay. So as you can see here, we have clock, we have reset, and then in data, out data. So the in data, these values are generated by using $random. So we have four different values, random values, and then these random values will be given or assigned to the out data, and we can see here the values is getting in the out data. Now at the reset, when the reset is high actified, the out data will be X. It will be unknown value, there is X. Now once the reset has been deasserted to active flow, you can see here the 4, okay, at the positive edge of the clock. That means here we are generating the 1 values by in data, okay. So this value will be assigned to the out data at the next positive edge of the clock. See here at 4, right? So it is a synchronous reset. So it depends upon the next positive edge of the clock in order to assign this in data to the out data. And likewise here in this positive edge of the clock, 1 is generated, but in the next positive edge of the clock only the out data is receiving. Like that, there is one clock positive, they wait for the positive edge of the cycle. Okay, so this is how the synchronized reset works. In the next video, I will be explaining you about the asynchronous clock. Thank you for watching.